Okay, cool. Do you see my screen?
Yes.
Okay. All right. Let's start with the absolute basic. So for some of you, it will be too boring. Feel free to grab a coffee or tea. Let's talk in general. What is atom? Atom has two main parts: a nucleus in the center and electrons around it. So an example on this example, atom has 11 protons, which is positively charged, 12 neutrons, which has no charge, and 11 electrons. So because the number of protons and electrons are equal, the atom is electrically neutral. The nucleus is itself, this central region, is extremely dense and contains almost all the atom's mass. Inside the nucleus, we have protons and neutrons, which I said. Then we are going to the another important concept of isotopes. So not all atoms of the same elements are identical. They can have different number of neutrons, and these variations are called isotopes. So the most simplest example here are isotopes of hydrogen. So protium, deuterium, and tritium. They have a different number of neutrons here, like 2 in tritium, 1 in deuterium, and 0 in protium. When you say hydrogen, typically it is protium because it's 99.98% of isotopes in the Earth. So it's when you call hydrogen, it's typically protium. Let's talk about but what basically hold nucleus together, protons and neutrons. So there are several important forces, let's say, inside the nucleus, but we will talk here about strong nuclear force and Coulomb repulsion. Strong nuclear force, it is extremely powerful at very short distance, and this is the force which hold nucleus together. And the Coulomb repulsion, it's happening between positively charged protons because they are the same sign. So they are naturally repel each other because they are positively charged. So a fusion is essentially the story of overcoming the Coulomb repulsion so that the strong force can take over and bind two nuclei into one. So let's talk about the energy. And here's one of the main concepts is binding energy. It is the amount of energy you would need to completely separate a nucleus into individual protons and neutrons. Or in other words, it's the energy that holds the nucleus together. And here we are coming to one of the main, let's say, concepts that's coming from the famous Einstein formula, E equal mc squared, that mass of nuclei doesn't equal to the individual mass of protons and neutrons. This difference is called the mass defect, and the missing part hasn't disappeared. It's converted into the binding energy. So actually, binding energy is equal to mass defect multiplied on c squared. And that's why the binding energy is enormous, and like nuclear energy, it's so power dense because speed of light it's very high. And that's why nuclear process release so much more energy than chemical. When we're talking about the nuclear, so now we're coming to the concept of nuclear energy. And typically, when people hear the words nuclear energy, they're just thinking about like one thing, like splitting heavy atoms like uranium 235 on the lighter elements. But nuclear physics actually gives two completely different pathways: breaking heavy atoms apart and bringing light atoms together. So let's slightly touch about both concepts. So on the left, we have fission. A neutron hits the large heavy nucleus like uranium 235, and the nucleus become unstable. And because it's unstable, it's split into two lighter fragments and release energy. Why does it release energy? Because the two fragment nuclei together have less mass than the original nucleus. And this extra mass comes out as an energy through E equal mc squared. On the opposite, we have opposite process fusion. When two very light nuclei, here is deuterium and tritium, they get close enough that the strong nuclear force grabs them and forms a new, more stable nucleus, helium-4, and neutron. And once again, energy appears, but for the opposite reason. The total mass of helium nucleus and the neutron is less than the mass of deuterium and tritium. What is important to understand, and you'll see on the next slide, is basically nature is doing the same thing. It's moving to more stable configuration. It's for the fission, uranium is unstable and is going to the lighter elements, which are more stable. In fusion, helium, it's more stable element than tritium and deuterium. And this is one of the most important charts in nuclear physics, the binding energy curve. This is the binding energy curve per nucleon on the y-axis and the mass number of nucleon. On the left side, so we see light elements, light nuclei, hydrogen, helium, lithium. And you can notice that the binding energy per nucleon rises very steeply as you go from the hydrogen up. That means when two light nuclei fuse and form a more tightly bound nucleus, the new nucleus sits high on this curve and it is more stable. And that difference in stability is what becomes energy. So fusion is simply climbing the curve upward toward greater stability. On the right side, we see the process which we described earlier, fission. So we have heavy elements like uranium, plutonium. So they're already near the top of the curve, but sitting on the downhill side. If you split a heavy nucleus into two mid-sized nuclei, the products move toward the peak near iron. That increase in stability shows up as released energy. So fission is sliding downhill toward iron. And right on the top of the curve is like iron ferrum 56. This is the most stable nucleus in the universe. Fission needs almost no input energy. Heavy nuclei like uranium, they're already unstable enough that just absorbing one slow neutron is enough to cause them to split. Fusion is the opposite. Light nuclei repel each other strongly. So to get them close enough for the strong nuclear force to take over, you need to input enormous amount of energy. High temperatures, high pressures, or both. But once you overcome that barrier, fusion gives you the highest energy density processes we know. So as you see here, for example, binding energy released per nucleon is far higher in the fusion reaction, is far higher than for the fission reaction. It's almost 10 times. But then the question: can we? Because on this part of the chart, so we have many different elements. So can we fuse any of them? And the answer is there are a number of constraints for the fuel that should be considered. And then we are coming to only the four viable reactions which are currently considered for the fusion. So first requirement is energy in and energy out. So the energy provided to nucleus to overcome the Coulomb barrier must be achievable, and the output energy should be large enough for the reaction to be efficient. And the next requirement is a probability. In nuclear physics, in fusion, the probability is measured in a so-called concept of cross-section. It is the effective area presented by nucleus to an incoming particle that results in a fusion reaction. Think about it as just about probability, because not if two nucleus of hydrogen of deuterium and tritium, they collide, they not on 100% generate fusion reaction. On 99.999%, they will collide. They will not fuse. So we will take a look on this later. So here is the fusion cross section of the different reaction. This one is deuterium tritium. This is deuterium deuterium. This is deuterium helium-3. And this graph explains to you why deuterium tritium reaction is one of the most popular reaction that are pursued by fusion startups. This reaction provides this is like the highest probability. It peaks on the lowest temperature than other reactions. This continued discussion of what are the potential choices for the fuel, and here you see like different reasons. Here's like different combinations of different reaction. So this orange part, the reaction is not feasible. Column barrier is too high, so fusion is impossible. This reaction cross section is too low, so fusion is impossible. So theoretically feasible is only small. It's only several reactions, which we will consider, which we will take a look on the next slide. So here, the most when you will hear about like discussion about fuel, you will hear about only these 4 reactions, or even only about 3: deuterium tritium, deuterium helium-3, and proton bore 11. So the most popular one is deuterium tritium. During the fusion, it's released atom of helium-4 and high energy neutron. It's released one of the highest energy gain per reaction with the lowest temperature among all possible reactions. The problem of this reaction is high energy neutron, which will activate materials and make it radioactive. The next reaction is never considered, at least at the current moment, as a commercial fusion reaction, deuterium-deuterium. First of all, because of the very small energy gain, temperature required for this reaction to happen not so high compared with other reactions, but energy gain is small, and it's also the probability, it provides a 50% probability of the outcome. That outcome will happen with the tritium and proton, or helium-3 and neutron. So basically, what does it mean? That within the reactor, you will have tritium and deuterium, which will generate deuterium, which will make deuterium-tritium reaction. So you will have a number of several fusion reactions, which will make this quite complicated. Deuterium helium-3, it provides the highest energy gain with a higher temperature required. It will not provide direct, so it's a neutronic reaction. It doesn't provide direct neutron from the reaction, but because of the participation of deuterium in this reaction, and because the temperature is quite high, deuterium-deuterium fusion will happen. So therefore, it's not completely aneutronic, so neutrons will be produced from the side reaction of deuterium-deuterium. And one of the biggest challenge of this reaction, that helium-3 does not exist on the Earth. It should be produced from other nuclear reactions. So it's a big question where this fuel will come from for the commercial power plant. And the last reaction, so this reaction, for example, there's one startup which is Helion. So they're trying to use this fuel. And the last one is proton bore 11. So this fuel is pursued by several startups. The most famous one is TE Technology. Well, it's with the energy gain, it's quite high, but it requires enormous. The reaction should achieve enormous temperature to make reaction happen. Then let's go back to the question of probability. So basically, as I mentioned before, when two atoms they meet each other, let's say, they don't fuse. They don't fuse on in 99.999% cases. Most of the time, so-called Coulomb scattering happening, which prevent atoms to fuse. So as you see, this is cross section of deuterium tritium fusion reaction, and this is cross. Let's say it's probability. So probability of Coulomb scattering of the collision, it's much higher than fusion. So that's why you need to give as many chances as possible for fuel to stay as long enough to get many chances, and this is called confinement. And if you will confine particles of these energies long enough, it will create conditions called of plasma. This plasma, it is in the plasma, electrons are stripped from the nuclei of the atoms, and to result in ionized gas, where positively and negatively charged particles move independently. So, and because of this concept of confinement, we are coming to very important criteria for fusion. It's called Lawson criterion. So we talked about cross-section, scattering, confinement, and it all comes to the these three main parameters: plasma density, how many particles are available to collide in the fusion reaction; T, plasma temperature, how fast the particles can move, so how much energy each collision has; and tau, energy confinement time, how long we can keep plasma hot before it loses energy. So multiply this together, and you will have so-called triple product, and this is one of the most important criteria to achieve to get positive, let's say, fusion, positive Q more than 1 fusion energy output divided on energy input. And this graph, so on the y-axis it's density, on confinement time, on the x-axis is temperature. So basically the red, and this one is Q equal 1, or in this area is Q more than 1. And all the fusion startups, they want to achieve this. And we will talk about this a bit later, that let's say for the magnetic confinement, the key parameters, confinement time is important for tokamak and stellarators, but for the laser inertial confinement, the plasma density is the confinement time is very short, but the plasma density is very high. So that's why the triple product may be the same as in tokamak, but it will exist for the very short confinement of time, but with a much higher plasma density. Bunch of different fusion approaches. We will not talk. It may take like hours of talking about all of them. Though we can split them on three main categories, three main types: magnetic fusion, magnetic inertial fusion, and inertial fusion. So here, this is basically the evolution of fusion concepts. Here, for example, like red one, and this is the progress of the fusion concepts in getting triple product. And the red line here is this is Q equal 1, Q scientific, so energy out equal energy in. So the first let's say key validation of the fusion reaction is to achieve energy gain. So at the current moment, only laser inertial confinement achieved Q equal 4 in the recent experiment in the National Ignition Facility. But most of the other approaches, they get quite close in the past to achieve Q equal 1. And some of the future devices like ITER, which is international projects, which is tokamak, or SPARC, which is developed by Commonwealth Fusion System, they engineered for the Q equal 10 or 11 in some, for the SPARC. So in the recent years, we will see some, we hope, let's say, to see progress in this area. So it's not only laser inertial confinement will get Q more than 1, but other approaches as well. And just have small short video to get just general understanding of how does it work.
We're not getting audio yet.
You hear the sound?
No, there's no audio yet, Sergey.
Okay, wait a second. Let's see.
And results of Lawson's criteria, there are essentially two options for achieving an economically viable. And results of Lawson's criteria, there are essentially two options for achieving an economically viable fusion. The first possibility is to maintain a relatively low density plasma for a longer period of time, which is the basic principle of magnetic confinement. The second option is the opposite and consists of keeping the plasma for a shorter time but with a significantly higher density. This is used in inertial confinement. The conditions for the successful development of fusion reactions are the achievement of the necessary product of plasma density and confinement time and the achievement of a specific ignition temperature at which the given reaction can take place. These conditions result in two basic types of confinement: magnetic and inertial. In magnetic confinement, the plasma is enclosed in a reaction space formed by a magnetic field, where charged particles move along closed field lines and are heated to the fusion temperature. The magnetic field is chosen in this case because no solid material could withstand such high temperatures. Relatively lower plasma density is characteristic for magnetic confinement. On the other hand, the confinement time ranges from tens to hundreds of seconds. Tokamaks and stellarators are based on the idea of magnetic confinement. Tokamaks created an additional toroidal magnetic field excited by an electric current flowing directly through the plasma. The most famous tokamak is the International Thermonuclear Experiment Reactor, ITER, which is being built in Cadarache, France. Stellarators, unlike tokamaks, create a suitably shaped magnetic field by adding external helical magnetic coils, usually of a very bizarre shape. Stellarators could work continuously in the future, whereas tokamaks are more pulse facilities. During inertial confinement, it is about achieving a short-term high plasma density by compressing a pellet of thermonuclear fuel using a beam of radiation, most often generated by a powerful laser. After evenly compressing the fuel pellet from all sides, the density and the temperature of nuclear fusion is reached in its center. But the compression and heating is so rapid that the fusion ignition occurs before the fuel is dispersed. The very high density allows a significantly shorter confinement time according to the Lawson criterion, which can be in the order of nanoseconds.
Okay, guys, that's